Log on, tune in, find out. Another good idea from Cambridge.
I should have Andreas Gustafsson, who's currently in Seoul University. And he's going to talk to us about ABJM with n equals 8 and supersymmetric enhancement. Is that right?
Yes.
Great.
So I will start with U1 times U1 ABJM and shown Simon's levels Kn minus K. And for K equal to 1 and 2, this says n equal to 8 supersymmetry and S to 8 R symmetry. So I will begin with this case. So I consider the Lagrangian.
Sorry, could you please make it a little bit larger?
Okay. This is a covariant, gauge covariant derivative. And A is running from 1 to 4. Now I define a new gauge fields here. And field strengths I define like this. Now if one has a Dirac, if one define also f1 is equal to d a1 and f2 is equal to d a2, one could expect one has Dirac charge quantization conditions. Like this, and then one can wonder what happens with f and g. So this is a lattice, like such thing. F1 and F2, yeah. And then I make a rotation here, 45 degrees. This is 45-degree rotation. And rescaling. And in that case, I get such a charge lattice here. And another one here. So I conclude that the charge quantization condition is 4 pi m plus nu and 4 pi n plus nu. Nu is either 0 for this lattice and 1/2 for that. Now I claim that ABJM theory is defined as only this, that is. So I define ABJM theory like picking this, that is, which means that the charge quantization is 4 pi integer. So I conclude that it is 4 pi integer. Then the Lagrangian is k divided by 4 pi df minus d. And the covariant derivative is
So please try and keep writing bigger.
okay. Then the idea is to, instead of integrating over a in the path integral, I want to integrate over f. So that means one has to add this term where sigma is periodic. I should write bigger, right? Okay. Then if one integrates out f, one gets kb equal to d sigma. And Lagrangian becomes this one can rewrite this as d mu x a, where I define x a as exponent minus I sigma divided by k, and since sigma is 2 pi periodic, this is identified with 2 pi I divided by k xa. So one has a sigma model on C4 divided by zk, and this orbifold preserves S8 symmetry when k is equal to 1 and 2. Okay. So S8 can be decomposed into, so S8 acts on XA as like maybe another name on this eta, and this is like U4 times U1, and this is the rest, which are in total generating S8. So eta is antisymmetric. and omega is anti-Hermitian. So together they generate SO8.
Andreas, there was a question. What happens if you take k not equal to 1 or 2?
Yeah, I'm going to answer.
You're guessing there.
I'm trying to answer. So SO8 should commute with this orbifolding. I call it operator O, which is delta O should be O delta, where delta is SO8 rotation. So that means that delta exponent 2 pi I divided by k xa should be equal to and if I make SO8 rotation on this one, I get and that means that 4 pi I divided by k must be equal to 1, and that means k equal to 1 over 2. Now I would like to see this supersymmetry enhancement in ABJM theory without doing this rewriting in terms of sigma model. So in the ABJM theory, this set A has U1B charge plus 1, and the complex conjugate has -1. And it means that one cannot consider such a transformation because it's not gauge covariant. So what one needs to do is to insert some monopole operator such that this combination here has U1 charge plus 1, just like this one. The monopole operator is in this U1 times U1 ABJM, it's just given by this exponent I sigma. And to see that this is a monopole operator, one just notice that the conjugate momentum to sigma is F12 divided by 4 pi, which follows from the Lagrangian on the top of this upper blackboard here. So this in turn means that So this is 1-2 plane. So this monopole operator creates magnetic charge, 1 unit magnetic charge in the 1-2 plane from vacuum. Moreover, this monopole operator has a U1B charge, K, and it is obviously local because it depends on x in a one point x, and it is covariantly constant. So the covariant derivative is given by this, and acting on sigma here, I bring down sigma, so it becomes and this is by definition 0. Then supersymmetry then. For k equal to 1, I define gauge singlet like y. This has this has -1, so this has +1, so this has gauge charge 0. U1B singlet. And chi I is equal to then the supersymmetry variations read and they close on this equation of motion, and to really show that it is enhancement of supersymmetry, one needs to show that this also corresponds to the ABJM equation of motion, which is so one needs to prove that one gets the ABJM equation of motion. But that's quite trivial. By inserting this definition into this derivative, so one gets this one, and then one else notices that this one is equal to minus IB. So for k equal to 2, it should also be an equilibrium supersymmetry. But in this case, I cannot define gauge singlets, so I need to do something else. Because the monopole operator in this case is still the same thing, but for k equal to 2, this has U1B charge k, which is equal to 2. So supersymmetry variations I claim are equal to but I would like to add more to this, like minus omega where omega is given by this variation of the monopole operator. Now, in this case, since supersymmetry variation of B is vanishing and this monopole operator in fact can be expressed as KB by using this KB is equal to G sigma. So it means that supersymmetry variation of this monopole operator is vanishing, and that means that omega is vanishing. But in the non-abelian case, this does not need to hold, so I think that omega is non-zero in the non-abelian case, and that's why I want to introduce this in the abelian case also. Okay, so now I will turn to non-abelian ABJM. And I will use three-algebra notation, so I call it three-algebra ABJM, which is, by which I mean n equal to 6 supersymmetric Chern-Simons method theory. In this three-algebra language, one has a gauge potential, which is usually denoted like this one. As far as one only works with this tilde gauge field, everything is fine with the three-algebra language. But some problem arises if one tries to use a conversion like this one, because this may not always be true. I mean, there is some trouble here if one uses this one. So I will not assume that this holds. So I will drop that, and then everything is fine. But this means that I only will work with supersymmetry variations and not with the Lagrangian. And this problem arises because of U1 factors. Then I would like to have some monopole operator, so I have three-algebra generators, which I denote like this. So this is a three-algebra index, small a, And one may think on it as bifundamental matrix, so it's ij, so I is running from, if I consider un times un, then I is running from 1 to n, and j is running from 1 to n. And this three-algebra index is running from 1 to n squared. The monopole operator I would like to consider has two three-algebra indices, and it should be symmetric. And it should be gauge covariant, and it should obey some complex conjugation, is like rising and lowering three-algebra indices. And it should be some kind of unitarity condition. And it should be covariantly constant. So these are all the assumptions, maybe. I could which lead to n equal to 8 supersymmetry enhancement. As I would like to try to show now. So covariantly constant monopole operator implies that by commuting, and okay, I can get this relation, and that means that since this is f tilde somehow f, but one has to be careful with the three-algebra indices. So what this condition means is that this condition holds. Where I define this so consider some matter field with some three-algebra index. Then I have two ways to raise this index, either by a monopole operator and I will use the notation, this notation, and the other way is to use a complex conjugation, and I will use that notation for this. So I will denote complex conjugation explicitly by complex conjugation. Then I would like to consider some symmetry variation delta I xi, and I assume that these variations close among themselves into some algebra. Then I also assume that this variation close on the monopole operator. And by assuming this, I show that these variations close on this monopole dressed field, like this one. So closure means J I X I. So I need to compute them. I switched to 1 and 2 here because I only consider 2 variations. So I call them 1 and 2 instead of I and j, and I will compute this quantity. And so here omega I and by direct computation I can compute this quantity, and it turns out that this equals to 1. So the result is by assumption, I assume that there is a closure on this with lower b, and then there is xb so what I got is this one. And actually this is a closure relation. Because if I start with this one, then this with upper index is given by delta, and So the variation of this, let me call this ABJM field, and this is non-ABJM field, which is a monopolarized field. It's the same thing. The variation of such non-ABJM field is should be given by this expression if one starts with such a variation of the ABJM field, and then the thing was to check that one has the closure on the non-ABJM field, and this relation shows that one has the same type of variation of this. So this shows that one has closure on not. So the upshot is that if one has closure on ABJM field, one has also closure on non-ABJM field. I would like to consider now some more concrete symmetry variation, which is mixing ABJM field with a non-ABJM field. Some example of this kind of variation is like S8 rotation, where this is ABJM field and this is non-ABJM field. So this is S8. So it's important to understand how the non-ABJM and ABJM fields are mixing. Now I want to show that this can never be a symmetry variation unless one also adds some term where gamma has to be chosen to be 1/2. So now I will come to this section, which is identities, which is something I think no one has understood in this paper I wrote with Sojong. So I would like to explain this. So one starts with F tilde. So this I claim is one identity, which is a property of the monopole operator. So I mean it follows from this covariancy constant monopole operator. One directly gets this condition, and then just apply n equal to 6 supersymmetry on this condition. So if one makes a supersymmetry variation of this, one gets almost immediately something which looks like some identity. Now I need to introduce a notation here, but this is a three-algebra structure constant. And this is so set A and psi I are so-called ABJM fields, and set, or better right, these are non-ABJM, and complex conjugation is always moving both R symmetry and the three-algebra indices up and down. So I have such a thing, and so this is ABJM and this is ABJM. Both of these are non-ABJM, so it is identity which relates ABJM and non-ABJM fields. So these are ABJM. I can derive more such identities. There is one more which is very important. It's essentially there is some very general type of identities which read like where this three bracket is defined as the capital answer, it's like this one. So such an identity implies, for instance, that set A, B, set B, C, set C, D, F, B, C, E, F. And from this one could naively think one would conclude that this is antisymmetric in BCG. But this conclusion is wrong. Because one cannot eliminate the matter fields, because A is running from 1 to 4. And three-algebra indices are running from 1 to some n square. And it's quite obvious that this is much fewer equations, much fewer conditions than this if n square is bigger than 4. So one cannot derive much more equations from fewer equations. And by the way, if this equation would hold, then one would conclude that one would have just a SO4 gauge group, which is also, of course, wrong conclusion. I assume that the monopole operator is symmetric, so I want to say why I assume this. So WAB is symmetric. This was explained by Klebanov and collaborators. So in UN times UN, one has magnetic charge vector n1 to nn, which I may denote as Q, and then one has a Dirac charge quantization condition. And the claim is that the monopole operator transforms in a representation of the gauge group, which is given by a Young tableau which has k and 1 rows and goes down to k and n rows. So if the monopole operator would be antisymmetric, it would correspond to such the Young tableau, and that would correspond to charge vector, which is 1/2, 1/2, 0. And this is violating the Dirac quantization condition for k equal to 2. I get this one because kq should this diagram should correspond to kq. So a symmetric case is better, because in that case one would get instead 1, 0, 0. There has been some objection to this idea with covariantly constant. So is it really true that the monopole operator is covariantly constant? And this is the same as saying that the monopole operator is a Wilson line. essentially. Because I'm suppressing the indices at infinity, so there should sit some indices at infinity also. And I would like to suggest that one can define the monopole operator just by contracting the indices at infinity. This is in speculation. If a Wilson line does not depend on the person, it used to be so that the field strength is vanishing. And this is not the case in here, because in this case I have this condition. But on the other hand, if I define it like this, it is not really a Wilson line because I'm contracting the indices at infinity. So I don't think there is any obvious contradiction. It does. So instead of this flatness condition, I get a weaker kind of flatness condition. I think that's all I have to say.
Any questions?
Yep. So the monopole operators exist. The only problem is the covariant constants, which is not. I mean, you had this list of assumptions for the monopole operators, right?
Yeah.
And the only problem is that it's that you have to show that it's covariantly constant. It's the only open issue there with the existence of the monopole operator.
Yes. Yeah.
And you get these relations over just by applying with successive supersymmetry transformations and then equals to 6.
This one, such, yes.
You start from that, go to the size, then go to the sense.
And so this from n equal to 6 only, yeah.
Andreas.